Hello, Math 1341 Calculus 1 students. This is the second part of our review for test 1. And what I'm going to do is just work a second sample test. So it's good practice for us. My caution, just like in the last one, you'll see different problems on our tests. And please see Canvas for the full collection of review materials. But we get started with the first question. The first question has a part about continuity and then two parts involving limits. Well, in 1a, we have a piecewise defined function. We want to find the constant c that makes this function continuous at -2. Show our work. Okay, first of all, what is f of -2? Well, that is here, this part of the function definition. We have -10 divided by -2 plus 3, which is -10/1, or -10. To be continuous, we need the function value to exist. This does. We need the limit to exist, and then we need the two equal. And when we have a piecewise defined function, we really want to look at the limit from the left and the limit from the right. So the limit as x approaches -2 on the left, well, we use values less than -2, but approaching. And so we can just evaluate this. We would have -2 squared plus c, which is 4 plus c. And then the limit as x approaches -2 on the right, well, we use values bigger than -2 and approaching. And so we could just evaluate here. In fact, we did this above. This would be 5 times -2 over -2 plus 3. So this is -10. So in order for the limit to exist and equal the function value, we need the following. We need the limit from the left to equal the limit from the right. This would be 4 plus c is -10. And we get c equals -14. This would give this function as continuous. It would say the overall limit is here, -10, and that equals the function value. We have continuity at -2. Now, next question. You see, we have the same function. We want a limit at 0 and a limit at 5. Well, this function is continuous at 0, so I can just evaluate. This would be f of 0, which is -5 times the square root of 4 divided by -25. And you see, we get 1/5 times 2, so it's 2/5. Now, f of x is not defined at 5, but what we can do is just factor. So the limit as x approaches 5, the denominator factors. What's happening here, we get this indeterminate form, 0/0. And be careful, this does not mean the limit does not exist. It also doesn't mean the limit exists. It means you just have to do something. And the something here is factor the denominator. So we have x minus 5 and x plus 5. And up here we still have x minus 5. And then times the square root of x plus 4. Well, now we're in really great shape, because x minus 5 over x minus 5, we can just cancel. So we have a limit as x approaches 5 of just this part, which is the square root of x plus 4 over x plus 5. Now this is defined at x equals 5, and so we can just evaluate. We have the square root of 9 divided by 10. And this gives us 3 divided by 10. So these were those two limits. Now, moving on. This question is an average rate of change, an instantaneous rate of change type question. This type of question appears on every first midterm, and we will see it also on the final exam. So we want the average rate of change of this function f of x from x equals 2 to x equals 6. This would be f of 6 minus f of 2 divided by 6 minus 2. It's this change in f divided by change in x. And we can come to the side if we'd like, calculate f of 6, calculate f of 2, and then we can go back to the quotient part. Well, f of 6, 3 times 6 is 18. 18 minus 2 is 16. So we have the square root of 16 plus 5. This is 4 plus 5, which is 9. Then we want the square root of 3 times 2 minus 2, which is the square root of 4 plus 5. This is 2 plus 5, which is 7. So I'm ready to finish this problem. We have 9 minus 7 divided by 4. 2 over 4, or 1 over 2. That would be simplified fraction. So the average rate of change on this interval is 1/2. Now, moving on, we want the instantaneous rate of change of this function at x equals 2 using the limit definition of the derivative. We cannot use chain rule here, say. We won't get any credit for that. We must use the limit definition. And so let's write it. F prime of 2 would be a limit as h approaches 0. We have f of 2 plus h minus f of 2 divided by h. Well, I typically will start with the numerator. So we have f of 2 plus h minus f of 2. F of 2 plus h, well, we have the square root. We have 3, 2 plus h, and then we have minus 2. And there is a plus 5. And then subtract off f of 2. Well, you see we have it right here. F of 2 is 7, so minus 7. Let's take one more step with this to simplify some before we do anything else. Underneath the radical, you notice I have 6 minus 2, which is 4. And then I have 3h. So we have 4 plus 3h. Then I have a minus 2. The question becomes, how do I simplify this? Well, the strategy when we have radicals is we want to multiply by its conjugate, but we can't just multiply by the conjugate, we need to multiply by 1. So we take what we see and we put a plus. So this would be 4 plus 3h plus 2, and the square root of 4 plus 3h plus 2, like this. You see, this quantity is just 1, so I have not changed anything. Now, why did I do this? Well, look how nice this is. My denominator has stayed the same. Okay, it's just this. I will copy and paste. But my numerator, when you multiply, the outer and the inner cancel. You see the minus 2 times this and the plus 2 times this, these add to 0. So I'm left with the first, which is 4 plus 3h, and then the last, which is minus 4. Now, look, we have, this is h times something. In fact, it's 3h divided by this denominator, which is the square root, 4 plus 3h plus 2. 4 plus 3h plus 2. This is exactly what we want here, because now when I divide by h, I will have an expression defined at h equals 0. This was my entire goal. So let's do this now. F of 2 plus h minus f of 2 over h is this. The h over h is 1. Now I can take a limit as h approaches 0 of this expression. What do we get? I get 3 divided by the square root of 4 plus 2. So this is 2 plus 2. My answer is 3 divided by 4. So this was definition of derivative here. As I mentioned, there are no points for using a chain rule to calculate this. The last part of this question asks for an equation of the tangent line to this function at x equals 2. Well, we have all of the information here. So we know the slope. This is the derivative, which is 3 over 4. We know a point. This would be 2 comma f of 2. 2 comma f of 2. And we've calculated f of 2. F of 2 was, it's here, 7, or you can just calculate it again. So the point is 2 comma 7. So we have y minus y1 is m, x minus x1. Like this. This would be our answer here. Number 3, We want global extrema for this function on a closed interval. We have a continuous function on a closed interval. We are guaranteed to have both a global max and global min. Now, it's worth commenting, we see one function divided by another. This will be quotient rule. So this is the rule we will use to find the derivative. Well, let's get started. The derivative, f prime of x. When we do quotient rule, it goes denominator, which is x squared plus 1, times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. Why are we taking a derivative here? Well, we look for critical points in the closed interval. Critical points are places where the derivative is 0 or does not exist. So we have calculated the derivative. You notice that x squared is never -1, so it does not exist, doesn't happen with this formula. And in order to set the derivative equal to 0, I need to take one small step here to make the numerator a little bit nicer. We have x squared minus 2x squared, which is -x squared. And then we have plus 1. And then my denominator I'll just recopy all over this, which is x squared plus 1 squared. Now, the derivative is 0. When does this happen? So f prime of x equals 0. A fraction is 0 only when the numerator is. So this would be when minus x squared plus 1 is 0. Or x squared equals 1. Now, technically, x squared equals 1 has two solutions. It's x equals 1 and minus 1. But this one, this is not in the interval. So this is not, minus 1 is not in the interval. And so we do not use it for a global extrema or a global extrema problem. It's not in the interval. We make a chart at this point. So for global extrema, it doesn't really matter increasing, decreasing. That kind of information alone will not tell you about global extrema. What we need is highest overall y value, global max, lowest overall y value, global min. And we know, well, they must occur at critical points. So my endpoints are critical points. These are the x's. And then we just want y value, original function, y value. So maybe to the side, I can evaluate my function. Well, f of 0, this is 0. And f of 1, you notice this is 1 over 1 plus 1, which is a half. And finally, f of 4, we have 4 divided by 16 plus 1, which is 4 over 17. So let's put that all here. We have 0, we have 1/2, and we have 4 over 17. Okay, if we compare these, 4 over 17 is certainly less than a half. So here's the biggest number that I see, and here's the smallest number that I see. I have a global max of y equals 1/2, and this occurs at x equals 1. I have a global min of y equals 0. And this occurs at x equals 0. So this is number 3. We need to work with the second derivative here. Second derivative gives us information about concavity. Let's get started. Well, in order to get to the second derivative, I need the first derivative. This is power rule. So I have 2x cubed minus 16 times 3, which is 18x squared. Immediately move into the second derivative. This is what I'm interested in when I'm dealing with concavity. I have 6x squared minus 36x. Now, I'm going to change the color of this because we do not use it again. This was just a step in getting us to this, because concavity, as I said, second derivative. So the second derivative is 0. Well, let's factor. I can factor out what's common to both terms, which is 6 and x. We have 6x and x minus 6. Okay, so the second derivative First of all, the domain of this function is minus infinity to infinity. It's a polynomial. The second derivative exists everywhere. Really, we just need where is this 0? And this happens when x is 0 and when x is 6. Okay, so now we divide the domain, which is minus infinity to infinity, into open intervals based on where the second derivative is 0. And we can write the open intervals underneath. It goes minus infinity to 0, 0 to 6, 6 to infinity. Then I need to test the second derivative to learn about concavity here. Here I can test, say, x equals -1. Here I can test, say, x equals +1. And then perhaps I'll test x equals 7. But it's really up to you. You can pick a different point to test. The value of the second derivative will change, but not the sign. So now let's make our chart. We want to test. Well, here's the second derivative factored. So this is what I'm going to be testing here. And this will give me the sign of the second derivative. And I'm using -1, 1, and 7. Okay. At -1, 6x is negative, x minus 6 is negative, second derivative positive. At 1, 6x is positive, x minus 6 is negative, second derivative negative. Finally, at 7, 6x is positive, x minus 6 is positive, second derivative positive. So let's put these here. We have a plus, we have a minus, we have a plus. We're ready to make our conclusion here. Concave up, everywhere we see a plus, which is minus infinity to 0 and also 6 to infinity. Is concave down, everywhere we see a minus, which is 0 to 6. Inflection points. Well, you notice here at x equals 0, the concavity is changing. Concave up on one side, concave down on the other. And at x equals 6, the concavity is changing. Concave down on one side, concave up on the other. So we have two inflection points, 0 and 6. Here, this answers concave up, concave down, inflection points. The next question, this is where we just want to differentiate. Don't worry about simplifying. Let me take an initial step here. I'll leave this alone. Pi squared, x squared, we have x. Now, inside this function is the 1/3 power. So what are we given? We are given f is differentiable. And then we want to express the derivative of g and h in terms of, well, x, of course, but then also the function, the derivative will appear. So first of all, understand pi squared is a number. So when I go to differentiate pi squared, x squared, the part that has an x is the x squared. If I just get to pi squared x. Now comes the part that is a little bit more intricate. This is a product here. We have first, we have second. And so we would have the first times the derivative of the second. Maybe I'll write it with a cube root here. To differentiate the second, it's a chain rule. Derivative of the outside, evaluated at the inside, and then we need to multiply times the derivative of the inside function, which I have it written as a power. This would be 1/3 x to the minus 2/3. Okay, I am not finished. Let's move all this over. We have first, derivative of the second. Then second, which is f of the cube root of x, times the derivative of the first, which is just 1. You don't want to write the times 1. It's fine. 1 times anything is just itself. But this is it. This is this function, g of x, differentiated and not simplified. Next one. Now be careful with letter b, because we see a ln. We also see a e to the f of x. But we cannot simplify this. We have a sum on the inside of a log. The log properties don't say anything about a sum on the inside of a log. So we just have to use chain rule here. So first thing, looking at this, my inside function is inside of the log. So we have 1 over That's derivative of the outside. Maybe I'll do this in black also. Evaluated at the inside. And then I multiply by the derivative of the inside function. Well, the derivative of e squared is 0. That's also a constant. Just like pi squared is a constant, e squared is a constant. But when we go to differentiate e to the f of x, this is also chain rule. So it's derivative of the outside, evaluated at the inside, times derivative of the inside function. Just like this. This is our answer in 5b. Next one, we have an inverse function theorem question. This is super fun. So, first part, calculate f of 2. Okay. F of 2, we have 2 cubed. We have plus e to the 2 minus 2, which is 8, plus e to the 0. E to the 0 is 1, so we have 9. Now, immediately, this tells us something about the inverse function. F of 2 is 9, means f inverse of 9 equals 2. Maybe I'll put this as a note. In fact, we need this in letter B. Sometimes these questions seem strange, like why am I evaluating the function at 2? But it gives us information, because if you look ahead, we want f inverse prime of 9. Well, let's write out the formula. We will see we need f inverse of 9 in it. So f inverse prime of 9 is 1 over, it's f prime of f inverse of 9. And I will typically make this another color so you actually see it. From the last step, we've calculated this. F inverse of 9 is 2, so we want 1 over f prime of 2. Very nice. What's left? Well, we need to differentiate the function, evaluate it at 2, and take 1 over that. So here we go. F prime of x. This is 3x squared plus e to the x minus 2. Now, technically, to differentiate this part, you see we have this function up inside the exponent of e, which is more than just an x. This would be chain rule. However, the derivative of the inside function is just 1. So whether or not you write the times 1 or not is fine. But this is the case. This is the derivative. Now we need f prime of 2. This is 3 times 4 plus e to the 2 minus 2. So this is 13. And so my final answer is 1 over 13. And I'll write that here. Okay. Inverse function theorem. It's one of those things, as I mentioned in class, the first time you see it, it looks a bit intimidating, but the more you practice, we can succeed in these types of problems. Last question, logarithmic differentiation. Okay, let's get started here. How do we do this? Take the natural log of both sides. So ln y will be ln of this entire thing, which is the 4th root of x plus 6 times e to the x, and then all over x raised to the 7x power. Now, next step, use log properties to simplify as much as you can. So the first thing is, you notice I have a quotient. This would be a difference. And at the same time, I'm going to write this as a power. That's x plus 6 raised to the 1/4, because that's going to help me. Now we have a product, ln of x plus 6 raised to the 1/4 plus ln of e to the x. Maybe at this step, I will go ahead and realize I have a power here. This is 7x, natural log x. We bring the power out in front. Now, one more step in our simplification. You notice I have not differentiated anything yet. But one more step. This is 1/4 ln of x plus 6. This is, well, it's x ln e, which was, that's one way to see. You could bring the power out. We would have this, x ln e. Natural log of e is 1. But, you see, really, there's parentheses here. Also, you can just use the fact that e to the x and ln x are inverse functions. So this is just x. And then we have this, 7x ln x. All of this is still ln y. Now I'm ready to differentiate. I have simplified as much as possible. Okay, 1 over y, y prime. The left-hand side is a chain rule. Y is a function of x. So we have 1 over y, y prime. Now we have 1/4 times, take the derivative. We have 1 over x plus 6. Technically times 1, but it's fine, times 1. Now, the derivative of x is 1. Put a minus. Now we have product rule. 7x, ln x. We have a product of two functions. So we have first derivative of the second plus the second derivative of the first. Well, that's it. This is fully differentiated. The last step, though, we want to multiply through by y. So I can take all of this. This is y, copy, and paste. And then I just recopy. So I have 1 divided by 4, x plus 6. Now, what's left? We can simplify or we don't have to. You notice we have a plus 1, and this is a minus 7. X over x is 1. So this is minus 6. And then we have a minus 7 ln x. But you don't have to simplify. You could literally just recopy this exactly right here. And don't forget multiply by y. That would be fine as a final step. Okay, then we leave it like this. This is using logarithmic differentiation. We have calculated y prime. So this is the end of this test 1, sample test 2, the second part of our review. I would definitely go back and look at the first part and also look in Canvas for a third sample test. So thank you so much, students. Good luck on the test.